Welcome to EPG Pathshala, lectures on numerical methods. This is second module on eigenvalues and eigenvectors, and we are going to have the learning objective for today's module are we are going to learn some of these methods here to find eigenvalues and eigenvectors. The first method that we are going to learn is power method for computing dominant eigenvalue. Then inverse power method will be finding out eigenvalue with minimum absolute value, and then the Jacobi method for computing all the eigenvalues and eigenvectors. In the module 16 we discussed concept of eigenvalues and eigenvectors, number of basic results related to eigenvalues and eigenvectors of a real n cross n real matrix were discussed. Relevance of these methods in the real world application was emphasized, giving two illustrations, and in this module numerical methods for solving eigenvalue problems will be discussed. There are a number of methods available in the literature. We will be considering the three relatively simple methods, that is power method, inverse power method and Jacobi method. The power method, in the module 16 we have seen that the stability of the solution of linear system depends on the condition number of the coefficient matrix A, and this condition number is expressed in terms of the eigenvalue with the largest and the smallest absolute value, and therefore, it is desirable to find out the largest and the smallest eigenvalue or eigenvalue with largest and smallest absolute value for any given matrix A. Hence, so if A is in any n cross n real matrix having eigenvalues as lambda 1, lambda 2, lambda n, and we are considering here that absolute value of lambda 1 is strictly greater than all other eigenvalues. That means, we are arranging them in the order of magnitude here, but that may not be absolutely necessary. What I am saying is that this is the largest eigenvalue with the largest absolute value, and there is only one such eigenvalue. Now, because there is only one such eigenvalue that dominates other as mentioned here, then it must be real, as complex eigenvalues will always occur in pair, and when they occur in pair their absolute values are identical, and therefore, there will be two eigenvalues with the same absolute value at the highest level, and here it is not so, and therefore, we will be considering only real. So, this will be a real eigenvalue. Also, the eigenvector corresponding to such a dominant eigenvalue also must be real, because the eigenvalue is real and the eigenvector is also going to be real, and therefore, it is possible to make the computations by this particular method to find out such a dominant eigenvalue. So, in fact, maximum mod lambda j is called the spectral radius of the matrix A, which is of great importance in mathematics. The power method works under the assumption that the matrix A has eigenvalues lambda 1, lambda 2, lambda n, such that mod lambda 1 is strictly greater than all other modulus of the eigenvalues, and the matrix A has n linearly independent eigenvectors. So, that is also essential. Now, this can be fulfilled if your matrix, this will be possible if A has all n distinct eigenvalues. We have already seen such results in the previous module, that if eigenvalues are distinct, then the eigenvectors are linearly independent, and if A is symmetric, then also eigenvectors are linearly independent, but these two conditions are not essential. I mean, they are sufficient condition, but we can say that what is essential is we want n linearly independent eigenvalues, eigenvectors. Because of assumption 2, x 1, x 2, x 3, x n will form a basis of R n. So, therefore, if y 0 is any arbitrary non-zero vector in R n, then y 0 can be expressed as a linear combination of these vectors x 1 bar, x 2 bar, x n bar. So, that is C 1 x 1 bar plus C 2 x 2 bar plus C n x n bar, and if y 0 is selected such that y 0 dot x 1 bar is different from 0, then this coefficient C 1 has to be different from 0. And suppose the sequence y k bar is generated by taking y k bar equal to A of y k minus 1 bar. That means, you start with any arbitrary y 0 bar, take next vector as y 1 bar as A y 0 bar, then y 2 bar as A y 1 bar, and so on. So, you go on generating sequence of vectors y k bar using this matrix product, and then this y 1 bar will be like this, we can consider. So, what will be y 1 bar? Y 1 bar will be equal to a y 0 bar, where C 1 a 1 x 1 bar plus C 2 a 2 x 2 bar plus C n a n x n bar. And a 1 x 1 bar, you know that because lambda 1 is an eigenvalue and x 1 bar is corresponding eigenvector, a 1 x one bar is same as lambda 1 x 1 bar, and therefore, this will be equal to C 1 lambda 1 x 1 bar plus C 2 lambda 2 x 2 bar up to C n lambda n x n bar. And repeating this process k times. Now, if I do this k times, I will get that y k bar will be expressed as C 1 lambda 1 raised to k x 1 bar, C 2 lambda 2 raised to k x 2 bar, and C n lambda n raised to k x n bar. And therefore, if I take lambda 1 common, lambda 1 raised to k common, I can express this as C 1 x 1 bar plus C 2 lambda 2 by lambda 1 raised to k x 2 bar, and so on and so forth. Now, by the condition we have imposed on the eigenvalues, you know that absolute value of lambda j by lambda 1 has to be less than 1 for all j equal to 2, 3 up to n, and therefore, this will tend to 0 as k tends to infinity, and therefore, all these terms will vanish, and therefore, y k will be approximately equal to lambda 1 raised to k into C 1 x 1 bar for large value of k, because we can say that these are all negligible things, and therefore, we can say that y k bar will be approximated by this particular number y lambda 1 raised to k into C 1 x 1 bar. Since x 1 bar is an eigenvector corresponding to the dominant eigenvalue lambda 1, lambda 1 raised to k into C 1, because any multiple of x 1 bar is also an eigenvector. So, this is also an eigenvector corresponding to value eigenvalue lambda 1, and hence y k bar. So, therefore, y k bar is approximates the eigenvector of A corresponding to the dominant eigenvalue lambda 1 as k tends to infinity. So, not only we get dominant eigenvalue, but we also get corresponding eigenvector. Magnitude of y k bar will increase with k if mod lambda 1 is greater than 1, and decrease with k if mod lambda 1 is less than 1. So, we have not put any restriction on this mod lambda 1, and therefore, this magnitude may go on increasing if this is lambda 1 raised to k. As k increases, this will happen. To avoid this particular effect, what we do is, in the beginning itself we consider like this. To avoid this particular problem, the iterative formula of for y k bar is modified as y k bar equal to a y k minus 1 bar by norm of a y k minus 1 bar. Now, this also will make your y k bar as a unit vector. So, therefore, you always get a unit vector as an eigenvector of lambda 1. So, thus if y k bar approximates the eigenvector of A for lambda 1, then mu k, which is equal to y k transpose A y k bar divided by y k transpose y k bar approximates lambda 1. So, now this will give me the approximate value of the lambda 1, and that we can easily notice that if we consider here A y k bar will be equal to lambda 1 y k bar. So, lambda 1 comes out, and therefore, this will give me the lambda 1 as approximate value, approximation to the eigenvalue lambda 1. So, your we have already seen here that this particular number approximates eigenvector, and this particular number will approximate your lambda 1. The error after k iterations will be given by E k, that is the error term, which will be mu k I minus a into y k bar. So, mu k is the value here which is approximating your lambda 1. So, mu k into I minus a y k bar, and note that if E k is 0, what does that mean? That mu k will be the eigenvalue of A with an eigenvector y k bar. So, that is what we mean by this. So, we can always compute the error associated with the approximation here. Thus, the algorithm for power method is as follows. We have got inputs here. So, size of the system is one of the inputs. So, n, then real matrix A, that is A I j, I equal to 1 to 3 up to n, j equal to 1 to 3 up to n, and ensure that A I are different from 0 for all I. So, we do not want diagonal elements to be 0 for all I. Tolerance for the difference in the two successive approximations we are considering. So, see, whenever you are having any iterative algorithm, you ought to have some convergence criteria, and for that convergence criteria what you have to do is, if the two successive approximations are close enough to each other, then we stop the algorithm, and here that closeness is determined by the successive difference between the successive approximation. If it is less than c, we will say that we will terminate the algorithm. So, that tolerance limit we are considering it as small c or small epsilon in general we write normally. So, maximum number of iterations to be performed, because many times iterative methods may not converge, and therefore, we have to take care that we should write down that we should make trials only up to certain maximum number of iterations, beyond which we can conclude that the method is not converging. So, that is max iter, and initial guess to the eigenvector is also taken as input to dominant eigenvalue, that is we are taking y j bar. So, that is arbitrarily chosen, which can be selected randomly. So, y j equal to 1 to 3 up to n. So, this is your initial approximation to the eigenvector. The output of this particular algorithm will be dominant eigenvalue and corresponding eigenvector, which is desired, right. So, lambda and y j bar, which indication of the, or if it is not possible, if the method does not converge, will give some indication that the method has not converged. So, one of the two will be the outputs here. The iterative step here will be outline of the main algorithm is compute x bar equal to a y bar. So, we are first finding out x bar equal to a y bar, because you know that we start with y bar was already taken as an input. So, I start with x bar equal to a y bar, then for k equal to 1 to max iter I am computing x bar dot x bar, and then norm of x bar as square root of this, and compute y bar as x bar by norm x bar. So, every time I am trying to make that this y bar becomes an unit vector. So, this is required, as we already pointed out earlier. Then we are computing again x bar equal to y bar, and compute b equal to y bar dot x bar, compute c equal to y bar dot y bar, and lambda we are considering it b by c. So, compute error e bar equal to lambda y bar minus x bar, again we take the norm of this error. So, e bar dot e bar you find out. So, norm e bar will be square root of d, and if norm e bar is less than c, we will say that we have already reached the corresponding approximation, and therefore, we will get lambda and y j printed, and the algorithm will get terminated. So, what we are doing here is we are writing a for loop for 1 to maximum iter times. Again we are saying that we are computing a equal to x bar dot x bar. So, same process is repeated. Then you take norm x bar equal to square root of a, y bar equal to x bar by norm x bar. So, you keep on repeating this steps in every iteration. Compute x bar equal to a y bar, then compute b equal to y bar dot x bar, compute c equal to y bar dot y bar. So, this gives me lambda equal to y by y dot x bar by y dot y bar. So, that is what I get from here, and then compute error e bar as lambda y bar minus x bar, and then find out the norm of the error. If the norm of the error is less than c, we terminate the algorithm, otherwise we will continue in the for loop. Suppose this never happens up to maximum iteration number of times, then we will print that algorithm does not converge in the matrix in the max iter iterations, and we end the algorithm artificially. So, here the computation of x bar equal to a y bar is nothing but product of a and y. I am just writing down the details of these small steps. So, for I equal to 1 to n, x I equal to 0, and we are computing here for j equal to 1 to n, x I equal to x I into a I j into y j. You know how to compute this x bar equal to a y bar. Then this is second task is subtask we can say, and that is y bar dot x bar. So, if I want to take dot product of two vectors, then I can find out dot y x is equal to 0, and for I equal to 1 to n you add, go on adding the successive terms here y I dot x I. Similarly, compute y equal to x by norm x bar. So, that is y I equal to x I, each component is divided by norm x bar. So, that is third task, and compute error equal to e y, lambda y bar minus x bar, and that will give me for I equal to 1 to 3 up to n e I equal to lambda y I minus x I. So, these are the small tasks which are involved in this algorithm, subtask involved in the algorithm, and when you are trying to compute the time complexity of the algorithm, we will just see how much time all these subtasks are going to take. As in earlier modules, we compute the time complexity of the by computing number of arithmetic operations and number of comparisons and expressed in terms of A, the time required for addition or subtraction, M, time required for multiplication or division, and C, time required for comparisons. In some specific implementations, this algorithm has 4 subtasks we already seen. So, these times are taken with some specific implementations. This algorithm has 4 subtasks. Task compute x bar equal to a y bar requires what? N square into a plus m time. How you can look at this? So, this process is done for I equal to 1 to n. So, for j equal to 1 to n. So, there will be n square total iterations will be happening here, and in each iteration we have got one addition and one multiplication done, and therefore, I can say that time required for subtask will be n square into a plus m. Then task computing y bar dot x bar. So, that will again involve, and e bar equal to lambda y bar minus x bar, both will require n into a plus m times, and task compute y bar equal to x bar by norm x bar will need n into m times, because you can see here what is happening here. There is one division operation. So, n times m time for this. Then you can see here this and this. In this case, we are getting one multiplication and one addition, one subtraction and one multiplication here. So, like that you can always get that n into a plus m here, n into a plus m here, n into m here. So, that is how you get this small time complexities for these subtasks. In the main algorithm, the for loop for k is executed max iter times, and in each execution of the for loop, task 1, 2 and 4 are executed once, and task 3 is executed 4 times, and therefore, task 1 is also executed once outside the for loop, and therefore, total number of the total time complexity will be given by this. If s is the time required to take the square roots, then we will say that total time required will be this is for task 1, which is to be done outside the loop. So, n square into a plus m, then max iter times. So, whatever happens within the for loop. So, max iter times n square into a plus m task 1, then 4 times task 2 and 1 time task 4. So, that is 5 into n to a plus 1 m, then n dot m, and 2 square roots we have to take. So, 2 dot s we are considering. So, that is how, which gives us the time complexity in terms of max iter times. Now, max iter and n square, usually the time complexity is measured in terms of size of the algorithm, and max iter remains fixed and it will not depend on the size, and therefore, we can say that it is order of n square, but because if max iter is large and n is small, then max iter also will play an influential role, and therefore, I am writing it as max iter dot n square. That is my order of the time complexity here. So, this is asymptotic time complexity of this particular algorithm. Now, inverse power method, if you take the inverse power method computes the eigenvalue of A having minimum absolute value. Now, if you want the eigenvalue with minimum absolute value, one observation is very simple here, that if A is non-singular matrix, that means A inverse exists, then and if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse having the same eigenvector. And why this is so? Because if I take x bar equal to lambda x bar, that means lambda is an eigenvalue of x, eigenvalue of A, and x bar is corresponding eigenvector. Then I can multiply by A inverse on both the sides and divide by multiply by 1 by lambda. So, I will get 1 by lambda into x bar will be equal to A inverse x bar. Now, this in turn shows that 1 by lambda is an eigenvalue of A inverse with same eigenvector x bar. So, that is what we mean here, and hence lambda is an eigenvalue of A with minimum absolute value, then 1 upon lambda is the eigenvalue of A with maximum absolute value. And therefore, in order to determine the eigenvalue of A with minimum absolute value, the inverse power method computes the dominant eigenvalue of A inverse by power method and take its reciprocal. So, find out the take its reciprocal, that will be the eigenvalue of A with minimum absolute value. Therefore, the inverse power method works under the following assumptions. So, first assumption is that A has to be non-singular, otherwise this method will not work. A has n eigenvalues lambda 1, lambda 2, lambda n such that this mod lambda 1 has to be distinct from all others. So, it should be strictly less than mod lambda 2 and so on, and the matrix A has n linearly independent eigenvectors x 1 bar, x 2 bar, x n bar. So, this is this assumption is required for power method application, and therefore, all the three assumptions are required for working of inverse power method. The method can be divided into two parts. The first part, we compute the A inverse by some numerical methods, and the power method can be used on A inverse. So, instead of computing x bar equal to A y bar, we have to compute x bar equal to A inverse y bar, or compute x bar as the solution to the system of x bar equal to y bar. So, that means you know that in the power method the first step is x bar equal to A y bar. That first step has to be replaced by this. Now, when you are trying to find out this, nothing but you are solving this system of equation A x bar equal to y bar. Now, either you use methods for solving system of equations and find x bar from here, or you can find A inverse once for all and use that A inverse in the power method. And hence, we have to find A inverse in the first step and use it in the place of A in the algorithm for power method. Okay. So, to find A inverse, what we do is we are using Gauss-Jordan elimination process. This process we already discussed in the earlier module on systems of linear equations and very direct methods, and on the augmented matrix A I n cross n. So, what we are doing is that Gauss-Jordan elimination process we are applying on A I n cross n. When you are applying this method for solving a system of equation, here we are taking augmented matrix with A and B bar, that is right hand side vector, but here in order to find inverse I am writing here I n cross n. And this elimination process at the end, what will happen that the last n columns of the augmented matrix will give me A inverse. So, when the elimination process is over, I get this as my A inverse. So, whatever is matrix left in the last n columns, that is A inverse. Another approach which is followed in most of the books is to factor the matrix A as a product of lower and upper triangular matrices L and U. So, once you find out L and U, solving system of equation A x bar equal to B bar becomes easier by forward and backward substitutions, and therefore, this will be using normal books. Most of the algorithms will be giving you this particular way to solve the system in each iteration using this factors L and U, but we will be following this particular approach because we already discussed this particular method in. So, we will follow this particular approach, and your method, the algorithm will be like this. Iterate. So, first all the input and etcetera output will be just as already mentioned earlier. The iterative steps will be: 1, use Gauss-Jordan method to compute A inverse from augmented matrix A I, that is I is identity matrix of order n. Use power method on A inverse to find its dominant eigenvalue lambda and corresponding eigenvector, and then the eigenvalue of A with minimum absolute value is 1 upon lambda and the corresponding eigenvector remaining same. So, that is my straightforward algorithm for finding out this. Recall that the asymptotic time complexity of the Gauss-Jordan elimination method is order n cube. We already discussed that earlier, and that is not going to change much, and that of the power method is order n into matrix max iter, and if max iter is sufficiently large than n, the asymptotic time complexity of the power method is just as that of the power method, and therefore, we will say that the and if max iter is smaller than n, then our assumption that means asymptotic time complexity will be of order n cube here. So, that means we are not discussing asymptotic time complexity in details here, because we already computed the asymptotic time complexity of the Gauss-Jordan method as well as this. So, whichever is larger, that will give me the asymptotic complexity here, depending on how much value of max iter you are going to consider. So, the third method, that is Jacobi method, we are going to consider, and that is this method is finding out all the eigenvalues and eigenvectors of a real symmetric matrix A. Now, here we need real symmetric matrix. Since A is symmetric, all its eigenvalues are real and all its eigenvectors form an orthonormal basis for R n by theorems 4.1 and 4.3 of module 16. So, we have discussed these theorems in module 16, which will give me this particular result, that for a real symmetric matrix all its eigenvalues are real and all its eigenvectors form a orthonormal basis. Therefore, if X is a matrix whose columns are eigenvectors of A, then D equal to X inverse A x. Now, there is another result which shows this. So, if X is a matrix whose columns are eigenvectors of A, then D equal to X inverse A x is a diagonal matrix with all diagonal entries as eigenvalues of A, and this is by theorem 4.6, which was discussed in module 16. So, I was telling you that we will be using some of the results from module 16, and these are the main results we are going to use in this particular Jacobi method. So, therefore, the way to find out this will be nothing but you start with some matrix A and try to work out this X inverse A x iteratively. So, that you get this as a diagonal matrix, and whatever you get on this side will be the X will be the matrix of eigenvectors. Note that A and D have the same eigenvalues as they are similar matrices. You know that these are similar matrices. Therefore, whatever eigenvalues I get and eigenvalues of A are same. You know that diagonal matrix, the eigenvalues are just the diagonal entries, and therefore, all the entries in this D will give me the eigenvalues of A. Note that A and D have the same eigenvalues as they are similar matrices. The Jacobi method approximates X iteratively by a sequence of non-singular matrices P, so that P inverse A P approaches to the desired diagonal matrix D. So, every time you go on modifying P and you take P inverse A P, step by step will approach to matrix D. This is achieved by performing a sequence of orthogonal similarity transformations. So, these are all similarity transformations, and that is what we are going to do here. The algorithm begins with initializing P as identity matrix n cross n, and then what I am going to do is I am going to make all the upper diagonal element, because it is, see, this is symmetric. So, what I am going to do is upper diagonal elements if I take any A P Q, which is non diagonal element, I will be trying to make it 0. So, that the P inverse A P will approach to diagonal matrix. This is what we are going to do. So, what I am saying is in every iteration upper diagonal element A P Q we are considering. So, I am taking upper diagonal element because A is a symmetric matrix. So, if I do this here, the same thing will happen to the other element also, and therefore, what will happen that A P Q having maximum absolute value among all the upper diagonal elements of A is found. Then a rotation matrix R phi associated with the rows of P and Q, which is the n cross n identity matrix I n cross n, except that elements R P P and R Q Q equal to cos phi and R P Q and minus R Q P are minus sin phi. So, that means the 4 entries will change in the identity matrix, and which are these 4 entries will depend on the what are the indices of the non diagonal element. Here we are taking upper diagonal element of A, which having the maximum absolute value. So, we are looking at this element. So, these are the P and Q. So, we are taking PP, PQ, QP and QQ. So, that is what we are going to consider. So, now here we get RPP and RQQ as cos phi and RPQ minus RQP as minus sin phi, and then this becomes a rotation matrix actually. So, it is easy to verify that R phi is a orthogonal matrix, that is R phi inverse will be same as R phi transformation. That we can easily check by just multiplying by R phi transpose to R phi, you will get an identity matrix. Then the P and A are updated as P equal to P R phi. So, what we do is P we already started with, we are updating P by P into R phi and A as R phi transpose A R phi. So, we select phi such that the updated in the updated matrix, because this will be updated matrix of A, and in the updated matrix A, APQ will become 0. So, each that means element with the maximum absolute value in the initial A in the next iteration will become a 0 element, and that we can do it by appropriate selection of phi. The algorithm terminates when all the upper diagonal elements of A are 0, and hence all off diagonal elements of A are 0, because your symmetricity of the matrix is not changed, because we are multiplying by R phi inverse R phi on both the sides, and therefore, this matrix also remains symmetric. So, therefore, R 0 as A is symmetric, and when A reduces to a diagonal matrix, because after all the non off diagonal elements become 0, it will be reducing to the diagonal matrix, and that is what we want. So, we can get D matrix only after reducing all these elements to 0. Thus, the algorithm for Jacobi method is as follows. So, we take input as size of the system, that is n or matrix you can say, the real matrix A, that is Aij I equal to 1 to 3 up to n, j equal to 1 to 3 up to n. Ensure that A is real and symmetric. We must ensure this, because the method works only for real symmetric matrix we have as discussed here. There may be some other approaches for non-real symmetric matrices, but here we are working only for real symmetric matrices. The tolerance for the off diagonal element C, that means how less you want that off diagonal element. So, that is what we are going to consider as C. Output all eigenvalues lambda 1, lambda 2, lambda n of A, that is diagonal D will give me all the diagonal elements will be eigenvalues of A, and the corresponding eigenvectors x 1 bar, x 2 bar, x n bar will be the matrix x bar. Okay. So, that will give me this. So, this is my output. Now, my iterative step starts here. So, outline of the main algorithm will be like this. What are the iterative steps? So, initialize P by I n cross n, then find above diagonal elements A P Q having maximum absolute value. So, that is what we are trying to do here. So, while mod A P Q is greater than C, we continue doing this. So, what is that? Phi equal to 0.5 star arc 10 to A P Q divided by A P Q minus A Q Q. Now, this selection of phi make sure that my in the next iteration A P Q becomes 0. Okay. So, this selection will make sure that your A P Q in the next iteration will become 0, and that is how, and this can be worked out. This actually this formula can be worked out by finding out new A P Q and equating it to 0. From that you can get the phi value here. Initialize R as I n cross n. I am calling it as R. Earlier we have said it as P. I am saying here R. Then R P P, we are changing those elements R P P, R Q Q, R P Q and R Q P. So, first we are initializing it to the identity matrix, and then we are saying that R P P will be equal to cos phi, R Q Q will be equal to R P P. So, that means both these are same identical. R P Q is minus sin phi we are considering, and R Q P will be taken as minus R P Q. So, this will make sure that whatever rotation matrix that I want, I can get it from R. Then we find out P as a product of P R, because we have to find out what is the next iteration value of P and A. A will be considered as product A R. So, we want R transpose A R. So, I am first taking A and R product of that, and again I am taking product of this A, now newly constructed A, with R transpose. So, I will get ultimately R transpose A R. Find above diagonal elements A P Q having maximum absolute value again, and then go back into the iteration. So, as long as A P Q is not less than C, this algorithm will continue. So, print eigenvalue of matrix A R as A11, A22, because your ultimate A will become a diagonal matrix and the diagonal elements will become your eigenvalues, and print eigenvectors of A as column vectors of matrix P, where what is that P? P we are already considering it like this. So, probably what we will do here is, so P already initialized to I n cross n, this is the rotation matrix that we are considering, and then this P keeps on modifying. So, ultimately we will get value matrix P, and that matrix P will give me as the column vectors of this matrix P will give me the eigenvectors of matrix A. So, the Jacobi method works like this. Now, we can see here that how to initialize P. So, initialize P to identity matrix. So, what we are trying to do is I equal to 1 to n, for j equal to 1 to n, you write I, if I equal to j, P I j equal to 1, P I j equal to 1, and if else P I j will be equal to 0. So, just I am just elaborating those simple tasks, right. Find above diagonal elements with maximum absolute value. How do I get that? So, maximum equal to 0 I take for I equal to 1 to n, and for j equal to I plus 1 to n. So, that will be above diagonal search I will be doing, and if mod A I j is greater than max, you change maximum, and you also store the indices in P and Q here, other two. So, and you go on doing this for all these iterations, and then in the end I will get an element in the upper diagonal with a maximum absolute value. Compute product P R. So, product of the matrices can be done just simple product we have to do. We have to find out all the elements in the as sum of this kth multiple of row and a column, ith row and jth column. So, I am taking sum equal to initialized to 0, sum equal to sum plus p I k star r k j. So, product P R can be obtained like this, and similarly we can find out product R k and product R transpose A R and R transpose A we can find out. Only thing in R transpose A, I need R transpose element. So, instead of writing here R k I k, I am writing it as R k I. This is the element k I kth element of R transpose. So, that is how we will be computing all the other details here. The time complexity, if you want to find out, then initializing I n cross n, this requires n square comparison, and hence time required will be n square c. Find above diagonal elements as A P Q having maximum absolute value, this requires n into n minus 1 by 2 comparisons, and hence we will be considering and time required will be equal to c times n into n minus 1 by 2. Why? Because we are doing this here, comparisons all the time. Then task 3 is computing P, the product P R, which requires n cube additions and n cube products, and hence time required will be n cube into a plus n. So, that is what we will be getting that, and the main algorithm uses while loop, which is executed at most n into n minus 1 by 2 times, because of the upper diagonal elements are only this many, and in which in each execution of the loop task 1 and 3 are executed once and task 3 is executed 3 times, and apart from this it requires 1 comparison and 1 subtraction operation and 1 multiplication and 1 division operation. It also involves evaluation of sine, cosine and arctangent functions, and let a be the time required for that, then all this collectively we can say that the time complexity will be equal to n square c plus c into this plus this, and all that you can write down, and ultimately you can see here. So, we are writing for each of this time required, and you can see that it will be asymptotic time complexity will be equal to order n raised to 5, which is very large. So, this is your Jacobi method. Now, we are applying this method on the various examples. We already considered these examples in the earlier module. So, I am taking example 1 A as 1 0 minus 1 minus 1 1 0 0 minus 1 1, and we are applying all the three methods here on these matrices. So, we are considering computational issues we are trying to find out. So, first we are doing here power method outputs we are considering of MATLAB program. So, example 1 I get here. So, power method will computing the eigenvalue with maximum absolute value, and therefore, we are tracking these are the iterations that is happening. So, 100 iterations we are doing, and even then my residual is not going to 0 here, and therefore, we can say that the method does not converge right in 100 iterations. See, probable reason is, recall from the previous module that A has two complex eigenvalues with maximum absolute value, and hence the assumption number 1 in the power method fails, and therefore, this is happening. In example 1b, the matrix is given to be like this, and then we are trying to find out again applying power method, and we can see here that in the 100 iterations we are getting this 0 0 0 0 8 8 up to that level we are going, and therefore, we can see here that the method does not converge in 100 iterations if we take 10 raised to minus 6 as my tolerance limit. So, therefore, it does not converge, otherwise you can say that it would have converged, but this is not converging within that. And probable reason is, recall from previous module that A has two real eigenvalues with maximum absolute value, and hence assumption 1 fails, and therefore, again there is a problem. Assumption 1 example 1 C, and I will get here 1 C iterative within 2 iterations probably I am getting this residual is 0, and therefore, I can get y. So, your eigenvector will be like this, and the corresponding eigenvalue mu is equal to 1. So, that is what I get here immediately, okay, and the corresponding eigenvector will be this. The method converges in 2 number of iterations, and we get eigenvalue as 1, and this is eigenvalue. So, eigenvalue becomes 1, and this is my eigenvector 0 this. So, similarly, I am doing this for inverse power method. So, this is example 4 for power method, and again we are trying to get this matrix, and you can see that this power method. So, the method again let us. So, this is your what we are trying to do is the example number 4 5 3 2. This is the matrix that we are considering, and these are the iterations we are going through. So, your eigenvalues are going in this direction, and we are getting ultimately the eigenvalue becomes 10 here, and you can see here that the residual error becomes 0 0 0 0 1, and therefore, that will be 10 raised to minus 6. It converges in 18 iterations, and we get eigenvalue as 10 and eigenvector as this. So, the residual is NR equal to this. Now, the inverse power method if you do, and you apply the same similar all these matrices we are going to consider, and you can see here that matrix is singular to the working precision, and hence the method will not be applicable here. Example 1b, if you consider inverse power method will work here, and you can see that within 27 iterations I get the eigenvalue as 1. So, the method converges within 27 iterations, and the corresponding eigenvalue is mu equal to 1 0 0, and the eigenvector is 0 0 1. So, that is what we get. So, residual NR equal to this. You can see that this method works here, though the power method fails. The power method, because eigenvalues with the highest absolute value, maximum absolute value are 2, whereas eigenvalue with lowest absolute value is only 1, and therefore, this method works here. And similarly, example 1 C, the matrix will, because this is a clearly an singular matrix, and therefore, method is not applicable. We get the answer in 19 iterations, and the method converges in 19 number of iterations, and we get your value as the corresponding eigenvalue is mu equal to 2. The corresponding eigenvector is given by this, and similarly we have the Jacobi method, and Jacobi method works for the symmetric matrix only, and therefore, we are going to consider only one matrix, that is, this is symmetric matrix. So, example 4 only we are considering, and when you apply the Jacobi method, the eigenvalues are the diagonal entries of the diagonal entries here we get. So, 10, 2 and 4 are the diagonal entries, and that is what I get as this, and the corresponding eigenvectors are this here, and this here. And probable reason, note that A is symmetric, and hence all the assumptions are satisfied, and therefore, method works. Right. Conclusions, that assumptions of existence of strict dominance eigenvalue in the power method and similar assumptions for inverse power method are crucial. Non-singularity of the matrix A for inverse power method is essential, and the Jacobi method has been discussed only for real symmetric matrices. So, that is what we are saying. So, in the summary, we have seen in this particular module, we have discussed numerical methods for solving the eigenvalue problem of certain special cases. The power and inverse power methods are used to compute the dominant eigenvalue of a square matrix and eigenvalue having the lowest absolute value of n cross n real matrix having n independent eigenvectors. We also discussed the Jacobi method for finding out all eigenvalues and eigenvectors of a real symmetric matrix is discussed. The algorithms for these methods have been given, and their time complexities have been discussed, and the output of the MATLAB program implementing these methods have been discussed in the end. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you.